So the integral test. So what are we doing here? We're asking. So what did we do in A2? We had a series, right? We had a series, like the series from n equals 1 to infinity of 1 over 2 all to the n. And on this particular one, we said converges, right? So, and we could actually find the sum, and we got a sum of 1. So, but now we're going to say, can I find out if something converges or not without actually finding the sum? And in this particular case, we will get an upper bound or a lower bound on the sum, right? So this particular one, we could find the sum, but we're going to have some kind of expression like n equals 0 to infinity of 1 over n, and then we're going to ask, can we find this sum? Does it converge or not? Does this converge or not? Right? So in A2, we were finding sums. Okay, when could you find a sum? If it was geometric, right? If it was geometric and our radius, our multiplier was smaller than 1, right? Bigger than -1, smaller than +1. If we could find a sequence of partial sums, and those had a limit, and that nth term had a limit, and then we could also find divergence, right? Just by doing the divergence test. If I wasn't eventually adding 0, right? There's no way it has a sum, right? So does this converge or diverge is the question, right? And I'm writing this kind of out, right? I can't start at n equals 0 there, sorry. Anybody else catch that? I want to start at n equals 1 to infinity, and if 1 over n, and what do I get? 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc., right? Now, remember my test for convergence, right? My test, I'm sorry. I want to look at this in comparison to f of x equals 1 over x. Right? So there's f of x equals 1 over x. And what do you know already about the integral from 1 to infinity of 1 over x dx? What do you know about this one?
It's divergent.
Divergent by? By what? You remember?
P-series.
P-series. I need that 1 over x to the p. I need p to be, I need that power, right? It's not a vegetable or urine. 1 over, right, the p-series. I need that power to be bigger than 1 for this thing to converge. Now, I can draw in this series 2 ways. I can draw it in below or above, and I want to think about both. Okay, so I want to draw in my series once above and once below. Very good, 1 over x there. So notice I'm going to be putting a value at every tick mark, right? A value at every tick mark, right? My first term, my second term, my third term, etc. And so my base is 1, because that's how separate each of my indices are, and my height is going to be the height I get from, right, each piece here. So the first one I need a height of 1, second one I need a height of 1/2, next one I need a height of 1/3, and then a height of 1/4, right? So this is the 1 plus the 1/2 plus the 1/3 plus the 1/4, right, etc. Yes, you with me? And so when I'm adding up, when I'm taking this series and trying to find a sum, I can really think of it as areas, right? Where the height is the height of the value of the addend in the series, and the base is 1 every time. Now, what does this one tell me? This one tells me that the area under the curve is smaller than the area under 1 over x. The area under the curve 1 over x is bigger than the sum of the series. But that doesn't help me because the area under the curve is divergent, right? The area under the curve is divergent. Now, it's a little bit weird in that when I'm doing the integral, I'm actually getting this green area, right? I'm actually getting the green area, so I'm leaving out that first box. But the first box is a finite number, so no big deal, right? If I have any finite number of numbers, that's not going to change divergence or convergence in any case. Does that make sense? If I have something that adds up to an infinite amount and there's a leftover 1, does it change that it's infinite? No. If I have something that adds up to 5 and I have a leftover 1, does that change that it's convergent? No. So any finite pieces left over will not change my decision about convergent or divergent. Does that make sense at all? Does this picture make sense at all? So I know that green area is divergent, right? And now I have a bunch of areas I'm adding up underneath that are less than the green area, or less than the green area plus 1, right, in this case. But it doesn't help me. It doesn't help me. I can't tell if this is conclusive that this 1 over n is divergent or not. Okay. So what we do in this case is we change our rectangles. So we got 1, we got 1/2, we got 1/3, we got 1/4. And I'm not quite doing it justice. My left hand, sorry, I have to do that over because it's not good. The left hand is always going to come from the height. So now, look at my green area. That's my integral test. And look at the red areas that are left over. So this one now tells me what?
It's greater than the divergent sum.
Exactly. Since the integral from 1 over infinity of 1 over x dx is divergent, and the series from n equals 1 to infinity of 1 over n is larger, the series is divergent. So there's the integral test. That's simple. If I find a function that is the x world representation of my series, and then I check the convergence or divergence of that function using an integral. If my integral converges, the series converges. If my integral diverges, the series diverges. So on this one, I'm throwing you back into chapter 5. I'm going to give you some integral test of something that you're going to have to do by parts with, or partial fractions, or trig subs, or trig powers, etc. Right? So here's a way for me to give you a test on a material in chapter 8, but lets you save face from the material in chapter 5, right? So now you can show me you can do one of these integrals, right? You can show me now. All right, you couldn't do the partial fractions on the exam, but you can do the partial fractions on the midterm, but you can do it on the final. Then I can say I don't care about the midterm, right? I can say the midterm was a motivator for you to get something done, and then I don't have to count the score. It doesn't work the other way though, right? I can't if your midterm is higher than your final, I can't count the midterm for everything because I need you to be able to do the chapter 7 and chapter 8 material. All right, let's look back. Well, let's do another one, and then we'll look back on a question that we did yesterday, right? How is this doing? Are we feeling pretty good about this?
I'm just confused that you don't have to change anything else about the statement other than making it left-hand or right-hand rectangles. Or that's just okay.
Yeah. So if you look at my two situations, look at the boxes are supposed to be identical. This is one here, right? So this blue box is identical to this blue box. So all of the area of the boxes in both situations are the same. Okay. What happened to the blue area, right? So like we're saying that all the boxes are blue, right? But what's going on with the blue area in the first situation is I can tell that area is right. Everything. So let's just go from here to here, right? All of those blue ones. So not the first blue one. Those areas added up are less than the green area. But the green area is divergent, so I can't tell if my blue boxes are divergent or not. Right? When I got some height that gives me an area that's divergent, just because I have something underneath it doesn't mean it's also not divergent. Right? If that top area is infinity and that bottom area is infinity minus 1, I'm using that loosely, I can't tell in that situation that that area underneath is divergent or convergent. It's inconclusive. So I draw it the other way. And now it's really clear that the red area is above the green area, right?
So you just shifted it over one, and that's why you said it doesn't matter about that one.
Exactly. Now, I personally took a long time for me to get that. So what I always do is I always give you a convergent. Integral test. I will say exactly this. I will say, show the following integral is convergent. Sorry, show the following series converges using an integral test. So the divergent one is a little bit weird, I think, as a thought in year one, in day one of learning this integral test. But when it's convergent, it's obvious. Okay, when it's convergent, right? So I've got some function, right? 1 over x squared, and I'm comparing underneath it 1 over n squared, right? Obviously 1 over x squared converges, right? And so clearly, in this case, I'm always going to draw it under, okay? So if the higher one converges, definitely the lower one converges. So I don't know if you agree with me. It makes more sense intuitively when it's convergent as opposed to when it's divergent. Is anybody there? To anyone, except for Charlie nodded, I think. Yes. So because I think it should bother you a little bit. I don't ask you to show something's divergent with the integral test. I only ask you to show it's convergent. All right, let's look at a problem from yesterday compared to this integral test, right? And we're going to take that telescoping series we had, right, from yesterday, and show it. Now we actually found the sum of the telescoping series, right? So, but we can do one of these tests really quickly to find out if we should even do this telescoping sum, right? And so that's what I want to do, right? So I'm pretty sure my series, so we're doing an integral test here. And I'm pretty sure my series was 1 over n times n plus 1. Can anybody double check in their notes for me? I'll look in my book here.
Yes.
Yeah, that's it. And so we showed that this telescoping series is convergent, and we found the sum. What was the sum? Do you have it written there?
1.
1? Yes, I remember that. And I'm starting from n equals 1 to infinity, which is nice. So I'm going to compare this particular thing. So we showed this yesterday, right? It's a converging telescoping series with a sum of 1. So what we want to do is we want to just verify that the integral test shows us it is also convergent, right? We're going to verify that the integral test shows us it's convergent. And now if you think about it, so like what are some of these terms here? What are some of my terms of a sub n? Help me start writing out some of them. I remember we were doing it yesterday anyway. So 1 over 1 times 2 is 1/2, right, is the first one. And then 2 times 3 is 1/6, is that right? So it's 2 times 1, then 2 times 3, then 2 times, 3, yeah, 2. Oh yeah, 1 times 2, I got it. And then 3 times 4, and then 4 times 5, right? Oh, plus. No, that's fine. I'm just writing out the terms there. That's fine.
Yeah.
Yeah.
I think we solved it. Well, we solved it with we did partial fractions.
Exactly,
So
and we're going to do the integral the same way. Exactly. So I just wanted to get a picture of a couple of my terms here, right? I could simplify this for sure, right? 1 over 2, 1 over 6, 1 over 12, 1 over 20. Who cares? I don't have to keep going. Just want to get a picture of some of my terms. And I want a graph. I want to compare to the function 1 over x times x plus 1, right? So the heights are going to be the same here, right? This is what 1 over x squared plus x. Is that right? And that looks like a bell curve. Okay, it looks like some kind of bell curve. But we're going to go from 1 to infinity, right? And so we're going to get this particular area, and then we're going to be drawing in our under the curve version of, right, a box with an area of 1/2, a box with an area of 1/6, the box with it. So I'm going to compare that black area, right, with all of the purple area except for 1/2. Okay, yes, you with me? Okay, so we're going to do this with an integral test from 1 to infinity of 1 over x times x plus 1 dx. And obviously that is a limit. If I ask you for one of these and you don't give me a limit on the final, I'll say, well, they still didn't do it on the midterm and they can't do it on the final, right? So make sure you're give me a limit here from 1 to a, 1 over x times x plus 1. Can someone remind me of the partial fraction decomposition we got? I'm pretty sure it's 1 over
1 over x
minus 1 over, yeah.
plus 1.
Yep. So we save a little time today in that we don't have to do the partial fractions again. We did it yesterday, right? So this is 1 over x minus 1 over x plus 1. Do I still have everybody? Some of you might be asleep. Some of you just are fed up with Calc 2. Go ahead, David, tell me.
Well,
This
looks like what we had before, and we're going to get infinity minus infinity.
Wait a minute. Wait for me. Wait for me.
Okay.
Okay.
Sorry.
No problem. I agree. Initially, it doesn't look like it's convergent, right? But infinity minus infinity is one of those indeterminate forms. So when we have an infinity minus infinity, because there are different sizes of infinity, this is why it's in indeterminate form. And the 4 mathematicians that studied infinity minus infinity went crazy, okay? So be careful about looking it up. Infinity minus infinity, because there are different sizes of infinity, could be infinite or could be finite. And so it's one of these indeterminate forms, and in that case, we want to try and get a 0 over 0 or infinity over infinity, which means we're going to get an LCD. We're going to get we're going to turn this minus this into a single fraction that should give us a 0 over 0 or infinity over infinity, or if it's convergent, or something else if it's divergent, okay? So anyway, we're looking here at the limit as a goes to infinity of what? ln of x minus ln of x plus 1 from 1 to a. Everyone agree with that? Is everyone with me here every step of the way here? Hey, Ruse, are you with me every step of the way? Melky, are you with me? Josh, you with me? Adrian, you with me? Josh, are you with me? Thank you, everyone else. Josh is there. Thank you, Josh. Adrian, you there? Michael, you with me? Thank you. Adam, are you with me? He's not even here. I just wanted to see if a thumb up on a blank square of my screen. This particular solution from pre-calc, we know that we can turn this into a single ln, right? This is a limit as a goes to infinity of ln of x over x plus 1, right? And I don't need the absolute value because I'm only putting in numbers bigger than 1, right? So I can combine this into a single ln term. I need the limit on when I plug in a. And I don't need the limit when I plug in 1. So this is 2 plus the limit as a goes to infinity of the ln of a over a plus 1. Let's make sure you agree with me there. I just did some funky little manipulation there, but make sure you agree with me. I get a minus ln of 1/2, right? So that negative means reciprocal. So it becomes plus ln of 2. And then I just put the 2 out front, right?
Wait, could you explain that one more time?
Yes. You agree I get a minus ln of 1/2 here, right?
Yes.
But the negative means reciprocal. So I get the ln of 1/2 to the minus 1. So that's ln of 2. Right? That coefficient out front is an exponent to the inside of the ln argument, right? So a
Yes.
negative 1 means reciprocal, so I flip it. So I just get
Oh,
the 2.
okay. Yeah.
Yeah. And now this other piece, I'm ready for L'Hopital's rule, right? Because I've got the ln of infinity over infinity. So I'm looking at 2 plus the ln of the limit as a goes to infinity of a over a plus 1. Right? And of course that is 1 by L'Hopital's rule. Right? So I get 2 plus the ln of 1, which is 2. Right? Because ln of 1 is 0. How are we doing?
Sorry, where did 2 come from? I got ln of 2.
Yeah, that's what I was confused.
Oh, thank you. ln of 2. That's
Okay.
right. Thank you. Robert. Silly boy. Just gone too fast. Do what I say, not what I do, right? So, by the way, ln of 2 is about 0.69314718006, to be precise. So, the integral test converges. We already knew that the series converged because we actually found the sum, but the integral test is verifying, because sometimes defining the sum is very difficult. Now let's come back to the picture. Right? I got that black shaded area to be about 0.6931. Right? So the shaded area is approximately 0.69. But it includes everything but what? The 1/2, right? It includes everything but the 0.5. You with me? That shaded black area is covering all of my rectangles except for the 1/2. So, right? So what am I saying? The series, we know, is a sum of 1, but we're going to take off that 1/2 that we didn't include in it to look at the area of the green rectangles. Are you with me? I'm trying to show that the green rectangles are less than the shaded area, right? We know all of the rectangles add up to 1, but we took off 1/2, right? So the series minus first term is what I'm doing here, is 0.5. And now notice that my shaded area is bigger than the terms of the series underneath. Okay, so again, I'm emphasizing the area from the integral is an upper bound on the sum of the series. If the area from the integral is convergent, then obviously the smaller area is convergent. And that includes any leftover finite pieces. So even, right, because I drew my rectangles underneath, I had this one leftover piece that wasn't accounted for. But I just showed you that the black shaded area was bigger than the green rectangles, right? That area of the green rectangles. So integral test convergent means series convergent. Ooh, pretty heady. I think on every of my last 5 final exams in Calc 2, and I think I maybe have 7 final exams, there's an integral test on every one. Okay, so I like partial fractions on this. Obviously, I like an improper. So I get to take care of the improper integral, partial fractions, L'Hopital's rule, writing it as a limit. Right, it's a great question to help you show me that you can do the midterm material. So you make sure you do all those integral tests. Okay. I hope I'm motivating you here to show me. You're going to show me. You wait, Robert. You wait and see what I do on this final exam. Right. That's what I'm hoping. I'm stirring that up in you. That you're gearing up to show off, and to wow, just to make me write wow on the page. I love it when that happens. Yes, Josh. And I got the chat open now. Is that enough for you there? Josh, is that good there?
Professor, the screen is really, like, it's hard to see everything.
When did that start?
It just started.
Okay, I'll reboot at break, and it should be fine when we come back. So, Josh, you might need me to reboot before you can see anything there, because I did scroll down. I've got Desmos open. That's a killer.
Professor Kuhar, I have a quick question.
Yes, Caleb, what's up?
So